Now, how do we add two vectors in this component form? If we have vector A and vector B, we want to add them to, and A has x, y and z components as Ax, Ay and Az, B has Bx, By and Bz. So, this in the component form can be written as Ax plus Bx x cap plus Ay plus By y cap plus Az plus Bz z cap. How do we multiply a scalar with a vector written in its component form? A scalar A is multiplied with a vector Ax x cap plus Ay y cap plus Az z cap. That just gives a this vector. So, we have in Cartesian coordinate system x cap, y cap and z cap, they are mutually perpendicular. These are orthogonal vectors, and the magnitude of all these vectors, that is unit vectors, is 1. Therefore, we have x cap dot x cap equals y cap dot y cap, it is the same, equals z cap dot z cap is 1, and if we take dot product of two different unit vectors, that is x cap dot y cap, that is equals x cap dot z cap, that equals y cap dot z cap, that always becomes 0. So, in a more compact notation, we can write I cap dot j cap equals Kronecker delta I j. Now, I and j can take values from x, y and z. So, we can write I j belongs to the set x, y, z, and Kronecker delta function is defined as this is 1 if I equals j, is 0 if I not equals j. That is the definition of Kronecker delta. Accordingly, now if we make a dot product of A and B, so A dot B, where A and B are written in component form. So, that is written as Ax x cap plus Ay y cap plus Az z cap dot Bx x cap plus By y cap plus Bz z cap. Now, if we take a dot product between this part and this part, we obtain Ax Bx. If we take a dot product between this part and this part, because the dot product of x cap and y cap goes to 0, we get 0 here, and for the next one also we get So, the dot product between Ax x cap and Bz z cap, that also becomes 0. Then we come to Ay y cap. Its dot product with Bx x cap goes to 0. The dot product that sustains is By y cap. So, for that we get Ay By, and the dot product with Bz z cap for Ay y cap also goes to 0. Similarly, for Az z cap, we will have only the dot product sustaining is with Bz z cap. So, we get here Az Bz. That means the dot product that we are interested in becomes Ax Bx plus Ay By plus Az Bz. Now, if we take a dot product of vector A with itself, A dot A, what do we get as a result? That will, looking at the example earlier, we can write that it would become Ax squared plus Ay squared plus Az squared. If that is the case, then we can write that the magnitude of the vector A is actually square root of this part, Ax squared plus Ay squared plus Az squared, square root of this. Now, let us go for cross product in this component form. Because with cross product we get a vector perpendicular to the plane, therefore, x cap cross x cap becomes 0. Similarly, y cap cross y cap and z cap cross z cap are also 0. If we take x cap cross y cap, that is minus y cap cross x cap, as we have found out for any two vectors earlier, and this equals z cap in orthogonal Cartesian coordinate system. Similarly, y cap cross z cap equals minus z cap cross y cap equals x cap, and z cap cross x cap equals minus x cap cross z cap equals y cap. This will be useful later for performing any cross product. So, if we now perform a cross product between two vectors A and B, we can write it as Ax x cap plus Ay y cap plus Az z cap cross Bx x cap plus By y cap plus Bz z cap, and that becomes, going by the rules that we have set here, Ay Bz minus Az By x cap plus Az Bx minus Ax Bz y cap plus Ax by minus ay bx z cap. Now this expression, so the way we have performed cross product is by going through the relations we have set here in above, but there is a better way to remember it and represent it in a compact form, that's by making a determinant. So the cross product can be written in a determinant form as follows. A cross B with its Cartesian components can be written as a determinant x cap, y cap, z cap, ax, ay, az, bx, by, bz. This determinant. Let's see an example. Let's consider a cube of arm length 1 in Cartesian coordinate system. Here is our Cartesian coordinate system. These are the axes x, y and z. So this much is arm length 1. So we have the cube like this. Here is the cube, and we have two vectors. This is vector A and here is vector B. We want to find the angle between these two vectors, that means this angle, let's call it theta. So let's write down A in its coordinate form. If we look at it, we can see that A projected onto x axis will give us 1. That means its x component is 1 x cap. Projected onto y axis, there is no projection, it is 0. And if we project it onto z axis, that is also 1. So this is the expression, this is the component form for A vector. For B vector, the component form would look like, its projection onto x axis is 0, so 0 x cap, plus projection onto y is 1 y cap, and projection onto z is also 1, so 1 z cap. This is the form of B vector. Now if we perform a dot product of A and B using the component forms that we have just deduced, we have this A dot B equals 1 dot 0 plus 0 dot 1 plus 1 dot 1, that means it's 1. And we know that A dot B equals AB cosine of the angle between them. So let's find out the magnitude of A vector A. that is given as 1 squared plus 0 squared plus 1 squared, square root of this entire thing, that is square root of 2. For B vector, the magnitude is also the same, 0 squared plus 1 squared plus 1 squared, square root of this equals square root of 2. And now applying this equation here, we find that square root 2 times square root 2 times cosine of the angle, that is 2 cos theta, is 1. And if 2 cos theta is 1, that means cos theta equals half, that gives us theta equals 60 degree.